Uh, Good afternoon, class. Hope you're doing well. I had a pretty productive weekend. Uh, I spent a lot of time putting together the forge stuff. So pretty much everything is here. I got my tongs. This weekend. I got my cross peen hammer, 3-pound cross peen hammer. It's pretty heavy. Gonna get a shoulder workout. And I got my whetstone, which is basically it's just used to sharpen. So the only things I have left are I have to get a quench tank, which after you've forged the object, if you want to harden it, you have to heat it up and then cool it down really fast. That's called quenching. And so you quench it in oil, so you need a special container. Or I don't know, maybe just a big pot. And then I just need steel. I haven't gotten the steel yet, so probably this weekend I'll be I'll be pounding some steel for sure. Hey Rowan, hey Mina, hey Nick, hey Justin, hey Tim, hey Rourke. A couple of announcements here. Your AP exams, if you're taking it, are next Monday. So we're not going to have class Monday, Tuesday, or Wednesday. We'll just take a couple days off, and we'll resume Thursday. I'm going to have a review session on Sunday afternoon. But not a review session, but just if you have any questions, I'll be on the Discord. And any last-minute questions before the AP exam. And then today I'll be posting a straw poll in the CHL chat on Discord to see what you guys want to learn after the AP exam. So I'll give you a couple of options. All right? So that's my news. And so let's get into the physics. We've got the 2008 free response for mechanics. And we're going to start with question 1. Let's see what it says. All right, looks like maybe conservation of energy or something with friction. A skier of mass m is skiing down a frictionless hill that makes an angle theta with the horizontal as shown in the diagram. The skier starts from rest at time t equals 0 and is subject to a velocity-dependent drag force due to air resistance of the form F equals minus BV. Where V is the velocity of the skier and B is a positive constant. Express all algebraic answers in terms of m, b, theta, and fundamental constants. On the dot below that represents the skier, draw a free body diagram indicating and labeling all the forces acting on the skier while the skier descends the hill. Okay, so skier is going to have a drag force which goes opposite the velocity, so that's going to be minus BV. That's the drag force. Skier is going to have weight force, mg, and skier is going to have normal force. All right. So those would be the three forces. Part B, write a differential equation that can be used to solve for the velocity of the skier as a function of time. So if we look at the weight force here, this component of the weight force has to cancel out the normal force, or else the skier will, get pushed into the incline or will lift off the incline. So these two cancel out. So the only part of the weight force that is not canceled out is this portion right here. This angle is theta. So that is mg sine of theta. That's the component of the weight force that goes down the incline. Okay? So if we do net force equals ma, the net force is going to be mg sine theta minus the drag force. And then that equals ma, but to make it a differential equation, we write the acceleration as dv dt. So that would be the answer. Part C. Determine an expression for the terminal velocity of the skier. To determine terminal velocity, you basically set the acceleration equal to 0, because if you're at terminal velocity, you're no longer accelerating. And so we set that equal to 0 and solve for v. And we would get v sub t equals mg sine theta over b. All right, part D. Solve the differential equation in part B. To determine the velocity of the skier as a function of time, showing all of your steps. All right, sounds good. So what I'm going to do is divide both sides by m, first of all. So I have g sine theta minus b over m v equals dv dt. Then I will then I'm going to separate variables, so I'll multiply both sides by dt, and I'll divide both sides by this thing, so I get dt equals dv over g sine theta minus b over m v. All right. Then I'm going to integrate both sides. On the left-hand side, I'll integrate from time 0 to t. And when time equals 0, the velocity is 0, because it says that the skier starts from rest. And then it ends up with velocity v. So on the left-hand side, it's a really simple integral. It just gives you t. Integral of dx is x. And then integrating that, we're going to get log, natural log of g sine theta minus b over m v times minus m over b. Okay? So I'm going to multiply both sides by minus b over m. Okay. Do e to the both sides. And then I will solve for v. there you go. So that would be your final answer. On the axes below, sketch a graph of the acceleration of the skier as a function of time and indicate the initial value of A. Take downhill as positive. Well, I could just take the derivative of that. dv dt equals A. So taking the derivative of the first term gives 0. And then taking let me see, did I miss anything here? Why do I feel like I'm missing something? Let's see. Oh, I didn't. Maybe I didn't miss anything. Let me just look at this for a second. See if I did an integral wrong. But I can see. I made an algebra mistake somewhere. Alright, well, I'm not going to waste time, but what you would do is you would just take the derivative of that. If I take the derivative of that, I get e to the minus bt over m. So why do I say that that's not the right answer? Because it doesn't have the correct units. So I've made an algebraic error somewhere, and I'm having a hard time seeing where it is, but it's there. So I know it's going to bother me, but I'm going to move on. So graphing that, it's going to look like some kind of an exponential decay. All right? All right. Because I think it should be this. That's what I think the answer should be. Okay. Check that later. Flipping the page. Number 2. A uniform horizontal uniform rod shown above has length 0.6 meters and mass 2 kilograms. The left end of the rod is attached to a vertical support by a frictionless hinge that allows the rod to swing up or down. The right end of the rod is supported by a cord that makes an angle of 30 degrees with the rod. The spring scale of negligible mass measures the tension in the cord. A 0.5 kilogram block is also attached to the right end of the rod. On the diagram below, draw and label the vectors to represent all forces acting on the rod. Show each force vector originating from its point of application. Okay, so we've got the tension, which is right here. We've got 5 newtons from the hanging mass. We've got 20 newtons acting from that point right there. That's the weight force on the rod, and the weight force from the rod acts from the center of mass. And then we can't forget that the hinge has to apply a force as well, which I'll call F sub H. Okay? So I think that's all the forces. Calculate the reading on the spring scale. All right? So what I would do is I know that the net torque acting on the rod is 0. So to remind you of the formula for torque, it's F perp times R. And I'm going to use the pivot point as the left side of the rod. So what we've got is we've got 2 clockwise torques, the 20 newtons and the 5 newtons. So that would be 20, and they're clockwise, so I'm going to have them be negative. And they're also perpendicular to the rod, so there's no sine theta business or anything like that. So I have 20 times 0.3, because that would be halfway to the center of mass, because the rod is 0.6 meters long, minus 5 times 0.6. And then the tension, this is a 30-degree angle. So the perpendicular component would be this side, which would be T sine of 30 degrees times 0.6. So the net torque is 0 because the rod is not rotating. So that means that we get that T equals 20 times 0.3 plus 5 times 0.6 over 0.6 sine of 30 degrees, which is going to give 15. It's going to give 20 newtons as the reading on the scale. All right. The rotational inertia of the rod about its center is 1/12 ml squared, where m is the mass of the rod and L is its length. Calculate the rotational inertia of the rod block system about the hinge. So we're going to use the parallel axis theorem. Okay, so the inertia of the rod about the hinge is going to be equal to the inertia of the rod about the CM plus m d squared, where d is the distance between the center of mass and the hinge. Okay, so we know that the rod about the center of mass is 1/12 m, which is 2, times L squared, so 0.6 squared, plus m d squared. D is the distance from the center of mass to the hinge, which would be 0.3. Okay, so the let's see what we get. 0.24 kilogram meters squared. But we also have to add on the inertia. See how it says the inertia of the rod block system about the hinge. Okay? So we got to also include the block, which would be 0.24. That's the rod in the hinge, plus mr squared for the block. So we have plus 5 times 0.6 squared. Oh, that should be 0.5. And that equals 0.18. So we get 0.42 kilogram meter squared. All right. If the cord that supports the rod is cut near the end of the rod, calculate the initial angular acceleration of the rod block system about the hinge. So we're going to use Newton's second law for rotations. So the net torque is going to be the same as it was before, but it's going to exclude the tension term because the rope has been cut. So we'll have minus 20 times 0.3 minus 5 times 0.6. So that's the net torque. And then that equals 0.42 alpha. So that's minus 3, that's minus 6. So we have minus 9 equals 0.42 alpha, which would be minus 21.4 radians per second squared is alpha. That's it? Okay. Question 3. Let me see if I have any questions from you guys. I forgot to do the zero term for the natural log. Thank you. That was the issue. Thanks, Potato Master. Good catch. I'll go back at the end of the video. Okay. Actually, I'm going to go back right now. Okay, so this should be that plus b over m, or sorry, m over b natural log of g sine theta. So then this becomes this gets divided by g sine theta. This gets divided by g sine theta. Okay, so then this becomes 1 minus over m g sine theta. So then this becomes v equals 1 minus e to the minus bt over m times the quantity mg sine theta over b. There we go. So that's the actual answer. That's wrong. And then taking the derivative of that gives the answer that I thought it would be, which is g sine theta times e to the minus bt over m. And then the acceleration as a function of time is going to be an exponential decay. Like that. Starts out at g sine theta. All right, thanks for catching. All right, in an experiment to determine the spring constant of an elastic cord of length 0.6 meters, a student hangs the cord from a rod as represented above, and then attaches a variety of weights to the cord. For each weight, the student allows the weight to hang in equilibrium and then measures the entire length of the cord. The data are recorded in the table below. Plot a graph of weight versus length on the scale below. Sketch a best fit line. If the weight is 0, okay, so I'm going to annotate this. If the weight is 0, the length is 0.6. Weight is 0, the length is 0.6. If the weight is 10, it's 0.97. If it's 15, it's 1.24. If it's 20, it's 1.37. And if it's 25, it is 1.64. Right there. Okay. So there is our best fit line. Like that. So we can see that our best fit line has, if I look at this, it goes up 25 and it goes over about 1 meter. So that means that our, right, because look at it, it's about 25 over 1. Yeah. So the slope is about 25. So we have a slope. Now f equals kx. So the slope is just k. So that means that k equals 25 newtons per meter. Student now attaches an unknown object of mass m to the cord and holds the object adjacent to the point at which the top of the cord is tied to the rod as represented above. When the object is released from rest, it falls 1.5 meters before stopping and turning around. Calculate the value of the known mass of the object. Okay, so here's what we're going to do. This mass, once it's dropped, it's going to basically undergo simple harmonic motion. Let me think about this for a second. Actually, I'm just going to use energy. So the initial energy equals the final energy. The initial energy is gravitational potential energy of the mass. So we have mg times 1.5. Okay? The final energy is all elastic potential energy. So we have a conversion from gravitational potential energy to elastic. Now, so we have 1/2 k x squared. Now, how much was the band stretched? If it fell 1.5 meters before stopping, then that means, because the initial length of the band was 0.6, that means it stretched 0.9. Okay? So we can use this to solve for m. So we get m equals 0.68 kilograms. D, explain how far down the object has fallen at the moment it attains its maximum speed. So we know that maximum speed occurs at the equilibrium point. So where is the equilibrium point? The equilibrium point is where the net force equals 0. Okay? And if we think about it, we've got two forces. We've got an elastic force on this, and we've got a weight force. Okay? So the x value at equilibrium is mg, which would be 6.8 over k, which is 25. So that's 0.27 meters is the extension of the band when the mass is in equilibrium. We have to add the actual length of the band to that, so we get that it falls 0.87 meters when it reaches its maximum speed. Okay? I just explained why it is. Then I'm going to, so what I said verbally, and then calculate what that maximum speed is. So we're going to do the same type of calculation. We start out with gravitational potential energy. Okay? And we end up with kinetic energy. We end up with elastic potential energy. Now remember that the band is stretched 0.27 meters. And we also end up with a little bit of gravitational potential energy. So basically the remainder of the 1.5 meters is gravitational potential energy. So we're going to have 1.5 minus this, that's 0.63. Okay, and we can solve for the velocity. We get a speed of 3.8 meters per second. Okay, so that was a fairly easy free response, I felt. Thanks for watching, and I'll talk to you tomorrow. I'm going to be posting a little another remind message for you guys to fill out the straw poll so I can plan for what we're going to learn next after the AP exams. And yeah, so sorry I made that math mistake. I apologize. Have a great afternoon.